Today's lesson, section 4.2a, talking about the natural exponential function. So like we talked at the end of the last video, the number e is attached to exponential functions as well. It has its own function where we use f of x is equal to e to the x with base e. This is often referred to as the exponential function. So meaning we actually our scientists use the exponential value of base e to help them map functions that actually relate to more realistic possibilities, like mapping out a virus, or figuring out the max population of a certain species, or figuring out when certain things will, substances will decay or disappear so that we are not able to use them anymore. So some of those kind of things are possibilities. So first, example 1 wants us to evaluate the expression rounded to 1 decimal place. So if I plug in e to the 3.7 power, then I get 20.1. Okay. If I plug in 2 times e to the negative 0.53 power into my calculator, I will get 1.8. Okay, so those are pretty simple. Example 2 says to graph the following functions. F of x is equal to negative, or to the negative x power, and 3 times e to the negative 0.5 x power. Now here, usually I would tell you to use these numbers. Okay, you can use whatever numbers you want, but I picked these numbers because it gives you the best picture, and they're easy numbers to actually graph. If you're picking like 4, 5, and 6 all the time, sometimes it'll get you a good picture because of what your function is doing, but it may give you such high numbers that it's hard to graph, and all you get is really a straight line looking thing. Okay, so trying to stay around the y-axis as much as possible is a good idea. So now if you weren't going to use those, okay, because sometimes you're not going to have negative 1, 0, 1. So let's say if that negative x was actually x minus 2, okay, I would tell you to set that equal to 0 and solve, and so solving that would get you the value of 2, and then pick numbers on either side of 2, so you would have 1 and 3. Okay, so plugging in those numbers in to this function would actually end up giving you the negative 1, 0, 1 again before you did the e to whatever power. It's kind of like our sinusoid graphs that we graphed in chapter 5. I always had you adjust those values when you were doing your table, and then you would be able to get back to those normal numbers of 0, pi over 2, pi, 3 pi over 2, and 2 pi, so that it was easier for you to graph later on. Okay, so that's kind of what I'm doing here as well. So back to the numbers at hand. So plugging in negative 1, so then that makes it positive 1, so that gives me 2.72. If I plug in 0, that gives me 1. If I plug in 1, it gives me e to the negative first, which is going to be 0.37. Okay, so if I graph those, so okay, so plotting those gives me this kind of graph. Remember, there's a horizontal asymptote there, just like our other exponential functions that we were graphing with different bases for a. It's the same thing here. You have a horizontal asymptote at y equals 0, so we're not really going to cross it with our exponential functions. Okay, so now I want to plug in negative 1 into the function for b. So 3 times e to the 0.5 times negative 1 power that gives me 1.82. Here, if I plug in 0, 0 times 0.5 is 0. E to the 0 is 1, so 3 times 1 is going to be 3. And then plugging in the last one, 3 times e to the 0.5 times 1 power, that gives me 4.94. So graphing those, so then you get -1, 1.82, and then 0, 3, and then 1, 4.94. So here it's a little bit shifted up, so you don't get the same, like, get super close yet to the x-axis, but eventually it will do the same. It's just moved up because of this value of 3. You're multiplying, it kind of changes, kind of stretches it away from your x-axis. Okay, so here's one of those real-world examples a little bit. So example 3 says an infectious disease begins to spread in a small city of population 8,000. After T days, the number of people who have succumbed to the virus is modeled by the function of V of t is equal to 8,000 divided by 4 plus 1,596 times e to the negative 0.95 t power. Here they want us to figure out how many infected people are initially, or are there initially. Sorry for my English. So so that means that at time t is equal to 0. So when I go, I'm going to plug in 0 for t. So plugging in the 0 and the exponent there, 0.95 times 0 will be 0. E to the 0 will be 1. So that means I get 8,000 over 4 plus 1596. So then that gives me 8,000 divided by 1,600. Okay? So simplifying here, you could say 80 divided by 16. So V of 0 should actually give you 5. So 5 people should be infected initially with this infectious disease. Now I want to be able to determine the affected people after 1 day, 2 days, and so 1 day, 2 days, and 6 days. Sorry for the error there. So plugging these in, so the following functions would look like this with 1 day, 2 day, and 6 days in them. So then after I plug them in, I would get the following values. For V of 1, you would get 12.8, and so because you want people, you're not going to have 0.8 of people. And for viruses, it would probably be good to overestimate so that you're not missing anybody. Because even though it's a model, it's not going to be super accurate. So we would say 13 people here. For 2, you would say 32.996. That rounds up to 33 people. Okay, and then for 6, you would get 856.5, which that would round up to be 857. So in the end, they want to know roughly how many people are going to be infected about this or by this eventually. So if we take our function and we actually plug it in to our graphing calculator stuff, it actually shows from the table that by the time you get to about like 19 days, you eventually get to 2,000. And so then it kind of just tops off at that point. So you would say 2,000 people. Now, sure, if you graphed it, you probably have a window that doesn't really look like much, but let's take a look if it's a little bit greater here. So going further out, it actually tops off at the top because of the division that we've created in the beginning function, which is right there. So that's what makes this kind of wean off instead of continuing to go straight up into infinity. Okay, so that's kind of how scientists are able to make a model so that it can actually reasonably estimate the number of people that are going to have something. Okay, have fun.